This question is actually on the law of conservation of linear momentum. So here we have been given a cart of mass 1 kg, which is initially moving at some speed 4 meters per second. It collides with a stationary cart, which is a bigger 3 kg cart. After the collision, the carts stick together, and we need to figure out the ratio of the kinetic energies. Now, there are two ways to solve this question. Method one is the traditional longer approach, and method two is the shortcut. We will have to discuss both one by one. Method one is simply using the law of conservation of linear momentum, which is this. It states that the initial and final momentum are equal if there is no net forces acting on the system. So, for this question, we have to assume that the 1 kg cart as well as the 3 kg cart, both of them are one system. So, initial momentum and the final momentum should be equal. So, let's see how do we do that. Let me write P is the momentum. So, before the collision, this is the momentum before will be equal to the momentum after. And the formula for momentum is m into v. Before the collision, the 1 kg cart was moving with a speed of 4 meter per second. So momentum in the before case will be 1 into 4 plus the 3 kg block was stationary, which means the speed is 0. We can write 3 into 0. So 1 into 4 plus 3 into 0, which comes out as 4. This is the momentum of the entire system, but before the collision. Afterwards, what happens? After the collision, the carts stick together. So the masses will need to be added. 1 plus 3 will become 4. So afterwards, the mass becomes 4, but the velocity we don't know. So let's take that as x. So we will write 4 is equal to 4x, which means x is equal to 1, which implies that after the collision, both the carts are moving together with a combined speed of 1 meter per second. Now we need to figure out the kinetic energy after the collision divided by kinetic energy before the collision. So let's write it down. Kinetic energy after divided by kinetic energy before. Kinetic energy after the collision. So kinetic energy formula is half mv square. So in our case, after the collision, masses were added 1 plus 3. So it becomes 4. And the velocity was 1 since we already found that out. This is after the collision. But before the collision, what was the kinetic energy of the entire system? 3 kg cart was not moving. So kinetic energy for that cart is 0, but 1 kg was definitely moving. So we'll use half mv square for this cart. So we'll divide the whole thing with half. Mass is 1 and the speed of the cart is 4. So we write that as 4 squared. Now, if we simplify this equation, so this is 4 upon 16, which comes out as 1 upon 4. And that's why option C is the right answer for this question. So this was the first method, which was the longer approach. There is an easier way out. How to solve the exact same question using a shortcut. So let's see. All right, so I have pasted the entire image one more time here. We have to figure out the ratio of kinetic energy. Remember, in questions like this, we are using the law of conservation of momentum. So according to that law, the initial and final momentums are equal. So the value of P, the momentum, is equal to constant. Now the formula for kinetic energy we know is half mv square. Now some students have this habit of saying that kinetic energy is directly proportional to m. This is not true. So now let's go back to the basics of physics. If we are using proportionality, proportionality will only work if other parameters are constant. Let me explain how. Kinetic energy is half mv square. So I can say kinetic energy is directly proportional to the mass only if the speed is constant. Here, the speed before the collision and after the collision, they are definitely not equal. So we cannot use kinetic energy is directly proportional to m. So we will use another formula for kinetic energy, which is expressed in terms of momentum, which is p square upon 2m. Now we know the law of conservation of linear momentum. The value of p is a constant, p being the linear momentum. Now, since the value of p is a constant, 2 is anyways a constant, we can write kinetic energy is inversely proportional to mass. Now, this proportionality ratio we have to use. So, kinetic energy after the collision divided by, let's write kinetic energy after divided by kinetic energy before. This will be written as mass before in the numerator divided by mass afterwards in the denominator. So before the collision, what was the mass? It was 1 kg. We will not consider the 3 kg block as it is anyway stationary. So initially the mass was 1 kilogram. So mass before is 1. Afterwards, when both carts stuck together after the collision, total mass became 1 plus 3, which is 4. Hence, the ratio straight away we can find is 1 upon 4, which is answer C. So in this question, we have been given an object which is held in a position by a string on an inclined plane, and the angle of incline is theta. Now, the value of theta is increased from 0. So that means initially theta was 0, which means this particular surface was a horizontal surface initially. We need to check which of the statements is correct about the forces acting on the object as the angle theta is increased. And the options are talking about the tension, the normal force, and the weight component. So, how do we approach this question? Step one is to draw the free body diagram of this object. So, one force will be the weight of the object, which is going downwards. W is equal to mg. Then we have the normal reaction going this way, perpendicular to the contact surface. And the direction of tension will be along the string and going away from the object as shown. Now it's clearly mentioned that the object is held in position, so it's not moving, which means we can deduce that the net force acting on this object is equal to 0. So just from the first statement, we can deduce that the net force acting on the object is 0, which means forces should cancel each other out. And how do we do that? Again, using the component method. So if we break the W into components, one component of mg will go in this arrow and the other component of mg will go in this particular direction. So the angle is given theta. This is theta, the angle of the incline, which means this particular angle will also be theta. Hence, the component of mg, which is going parallel to the incline, this is mg sine theta, and the other component of mg, which is going this way, this will be mg cos theta. And now let us balance the forces. So the value of normal reaction should be equal to mg cos theta and tension should be equal to mg sine theta. So let's write it down. N is equal to mg cos theta and T will be equal to mg sine theta. Now let's look at the options one by one. Option A states the tension in the string remains constant. That is wrong because tension depends on theta. As theta keeps changing, as it is given in the question, theta is getting increased. As theta changes, sine theta changes, which means the value of T is variable. Hence, option A is wrong. Option B states the normal force decreases. Let's check that out. Normal reaction is equal to mg cos theta. So in this question, it is clearly mentioned that the value of theta is getting increased. So we need to check what is happening to cos theta. Since n has cos theta in it, so the value of n will either increase or decrease depending on what is happening to cos theta. So let's see how to check that. For that, it is important for you to remember the shape of the graph of a cos function. So the cos 0 is 1 and at 90 the value is 0. So the value of cos actually decreases when the value of theta increases. So let me write down as the value of theta increases, the value of cos theta that decreases as you can see from this graph. Now, since cos theta is decreasing, that would mean n will be less than mg. Let me write this clearly. Since n is equal to mg cos theta and the value of cos theta will be less than 1. Why less than 1? Because cos theta is equal to 1 at 0 degrees. But we have made sure that the theta value is increasing. So theta is not 0. So the value of cos theta will be less than 1. And now n is equal to mg cos theta. So we can write n will be lesser than mg. So basically we are comparing this equation number 1 with equation number 2. Cos theta is less than 1. That is why the value of normal reaction is less than mg. And in option B, we were supposed to check is the normal force decreasing. So if cos theta is decreasing, the value of n will also decrease, which means option B is correct and that is the answer. But in any case, let us discuss the other options as well. Option C. The weight component parallel to the slope remains constant. Let's check. So the component of the weight which is parallel to the slope is mg sine theta. Now again, theta is variable, it is getting increased. So sine theta is changing. So the weight component cannot remain constant. And hence option C is also wrong. Option D, the weight decreases. This is definitely wrong because the weight is equal to mg and that is a constant. That cannot decrease depending on the angle theta. And that's how we solve questions like this. The only step one which is important is to draw the free body diagram of the object. And step number two is to break the weight into two components. And then we use the net force is equal to zero and then try to balance the forces like we did.